our second session. So we have two excellent speakers, and we are going to start with Jian Huang. And he's going to talk about advancing statistical frontiers, leveraging large models in statistical analysis. We have 30 minutes, I would say, and yeah, I can give you a warning. Would you like a warning? Like
sure,
5 minutes.
5 minutes.
Right, 30 minutes, so let's say 25 minutes and then 5.
Okay.
Awesome, thank you.
All right, great, thank you.
Yes, yes.
All right. I want to thank the organizers for inviting me to come here and share. So I have this great opportunity to share some of our work. So today I'm going to talk about leveraging large models in statistical analysis. All right. So I want to just look back just a little bit about how statistics has been developed over, last 100 years. Of course, I won't get into that, but basically, I think in the mid 90s to early 2000, statistical learning and machine learning are actually indistinguishable. They are basically dealing with the same problem. Actually, I think machine learning or AI really benefited a lot from statistical learning, this data-driven kind of idea. But from around 2010, exactly 2012, since AlexNet came out, statistics and machine learning kind of diverge a little bit. In particular, AI and machine learning focus on mainly two things. One is deep learning, another is really reinforcement learning. Okay, and the result of that is main thing is large models. So what I've been thinking in the last few years is, can we use large models to help us to do statistical analysis? Very simple. Okay. Now this is my my own interpretation of Fisher. Okay. So I think Fisher really established sort of the foundation or how we view. Again, this is my own interpretation. Okay. Not it's not representative. I could be misinterpreting Fisher. But basically, as we know, statistics before Fisher, there are two things. One is real world, another is empirical world. Okay, so basically, Fisher says we need to have a theoretical model. So his paper, 1922, established. The title of the paper is on the mathematical foundations of theoretical statistics. I think our traditional or our current statistics is largely based on Fisher's framework. Okay. Now, of course, today, in the last maybe 10, 20 years, things have changed a little bit, right? Besides the data or our little world, my lab, my study, we also have this big world. We have this big data. Now we have large model. So the question is, can we use this, information from big world, big data, in particular large model, to help us to do statistical analysis. Okay. Now, actually, big data was came out maybe around 2010, right, after the internet data. But it's very, very difficult to use large data. Now, since large model came out, I think large model, my understanding, one of particular understanding is really a statistical summary of large data. So it actually provides us with a very convenient tool because it's really a statistical model. Okay, so it provides us with a very convenient tool to use in our analysis, in our statistics. Okay, so that's my overall perspective. Now, Hong Tu mentioned, many different large models, but if you look at the whole landscape, in biology, chemistry, physics, material science, climate, earth sciences, of course, healthcare and medicine, there are many, many different large models came out. Okay, and for example, in biology, AlphaFold and also ESM2, those are the two models we have some experience with. That's why I put it there. And then, of course, the large models for electronic health records data. Okay. So the question here is, how do we leverage or how to use this kind of large models in our daily statistical practice, right? Okay. So today, what I'm going to do is to really very, very quickly share with you a few things we have done, very ad hoc in some sense, a few examples that our own experience. Okay. So the first one is, I call that model-assisted analysis. It's basically use foundation models as a prior, okay? Kind of like thinking in terms of Bayesian approach, although I've talked to some people who are real Bayesians, they don't necessarily agree with me, but that's my own interpretation. The second one is use large models for data representation, okay? The third one is use large models for data imputation, in particular, generating synthetic data. So those are very, very very ad hoc way of looking at large models. There are many other ways of looking at using large models in practice. Okay, so those are just a few examples. Okay, first one is how do we learn a conditional distribution using large models? Okay, in a generative modeling framework. All right, so let's get back to the very basic, very standard, very basic stuff here. Okay, so suppose I have a large sample space. Okay, that's my very simplistic representation of large model, and then on that space I have a probability distribution. Okay, that's my large model, and then what we have here, the data I have in my lab is from a subset of it. So on this small space, the large model has a trace. Okay, we can also define a probability space and then define a probability distribution P delta there. Okay, that can be defined in terms of large model distribution as a ratio, right? That's really just a conditional distribution of P of any event, given that my data is coming from part of our large sample space. And of course, in general, we can write that because we don't want to work with events, we work with random variables, and we have this conditional distribution of my data with the condition here, C there, and then use Bayes' theorem. I can write, this is the conditional distribution I wanted to learn, okay? This is a large model. So Bayes' theorem provides us a very natural way of thinking using foundation model in our data analysis, okay? So basically, I have this prior information, and this is what I'm interested in. And in particular, in the generative modeling framework, as we know, the so-called AI today is really all generative models, right? So generative learning is a very interesting kind of idea. Okay, so I want to learn that conditional distribution. And then in the generative model framework, I want to learn this generator function so that it has this conditional distribution, okay? So for example, I'm going to use image data as an example. Given the condition, from a large model, if you don't consider this condition, that the data, the image you generated are not consistent with that condition. This one is consistent. Okay, so that is a sample from this conditional distribution. Okay. Now it turns out what's interesting is that this kind of generative model, one of the most important generative models is really the diffusion model. I'm going to skip all the sort of history here, but basically, what's interesting here is that diffusion model, again, I'm going to ignore a lot of details. I think most of you guys here are familiar with this. It's really, what's important is to learn the score function. Okay, score function is a derivative of the log likelihood function. So what's interesting here is that if you look at the Bayes formula, then the denominator, that normalizing constant, is gone. Okay, after we take the derivative. So so it's very naturally related to the formulation I just described. Of course, the most popular model is this DDPN, right? It's really a discretized version of the continuous diffusion model. By the way, diffusion models are not something new. It's been there for a long time. Actually, the basic idea actually came out from Kolmogorov in the early 50s. But in this paper, it has a very rigorous derivation of the based on forward diffusion and derived the reverse diffusion model, the reverse SDE there, so that you can sample from a Gaussian distribution to your data distribution. Okay, so so what I'm interested in here again is to learn that conditional distribution by sampling. Okay, so generative model is really a way of sampling from the distribution. So a sample from that conditional distribution based on the diffusion model. I won't get into the details here, but the basic idea here is very similar. It's essentially the same framework of the standard diffusion model, except that the denoising function here is this conditional expectation. Okay, so this blue-colored conditional expectation is based on the larger model. Okay, without the condition. Remember, in the Bayesian formula, we need to learn that conditional distribution. My color may be switched, but basically this is what we're interested in. This is based on the larger model. So basically, from a diffusion framework, if I already know that unconditional diffusion, that denoising function, that's going to be very helpful to me to estimate this conditional denoising function, right? So here, if you look at this equation, what in some sense, what it's doing here is change the task of a generative learning model to a classification task. Doing classification is much easier than doing sampling from a distribution. Okay. All right. So in this sense, what we can do is, well, I want to learn the conditional denoising function, and I know this diffusion large model. So I'm going to, I'm not going to retrain the whole large model. So I'm going to freeze it, okay, fix it, and then in this, because it's a conditional expectation, so the objective function we know in statistics we're just doing, least squares non-parametric regression, and I'm going to fix that model and then only learn the parameter in that function. Okay, so this is another way of describing fine-tuning in some sense. Okay, so I'm using the image data as an example because when you see the picture, you know what the results are, right? So for example, for image data, you have all kinds of different conditions. This image is consistent with this condition. This one is consistent with that. Okay, so those are coming with pairs and the data. I want to train a conditional generator to sample from this conditional distribution. Okay. So this is the work we did actually. It's mainly done by a student, Huang Ding. Later on, I will mention that. And then Li Ting. Li Ting is right there somewhere. Okay, back there. So basically, the large model is Stable Diffusion 2. This work was done like over a year ago. Stable Diffusion 2. Stable Diffusion is one of the 4 large image models. Stable Diffusion 2 is exactly based on DDPM. Okay, so this is the architecture. Essentially it's a UNet, but each layer is a attention layer to cross information between image and text description. Okay, what we did there is, have that I call it Bayesian power steering. So to modify each layer in this UNet, so it's each attention layer. Okay, so that's the training objective. I'm not going to get into the details, but really quickly just show you some pictures. So for example, these are the some of the images. This condition you can simulate or sample from this trained conditional generator. One point I want to highlight is that actually with a foundation model, the requirement for the sample size is much less. You don't need big data, huge number of data points. So for example, for this one, this is with the larger model, this is 2K, the sample size is 2,000. If you don't use the foundation model, it's very difficult to train a generative model to generate good quality images. For this here, we only need like 40 images to train this model, because I think in diffusion, stable diffusion, there are a lot of pictures of cat. Okay, different kinds of cat pictures. Okay, all right. So it seems to work pretty well, and we have comparisons with other 2 major systems in the market here. One is control net, another is T2I adapter. Those are two main things from big groups. So we can the images look reasonable. All right, so this is one way I think we can think about how do we use foundation model in statistical analysis. Of course, you can apply this for other data. All right. Second one, I'm going to go through this really quick, but basically, we have spent a lot of time on this model. Is something called continuous normalizing flow. Instead of stochastic differential equation, actually we have a ODE, ordinary differential equation. So the main thing is that the sample path is much more smooth. Computationally, it's easier to sample from this one here. Okay. So the basic idea is to have a stochastic interpolation between data and Gaussian noise. Okay, over the interval between 0 and 1. Once I have that interpolation, that's very easy to compute, and I'm going to construct this ODE here. Okay. The randomness of this ODE is from the starting point, from the Gaussian distribution. Okay. And with this is called velocity function defined as this conditional expectation. Then you can show that if you sample from 0, starting from 0 based on this equation, okay? If you know this one here, starting from 0, you go back to 1, then the sample is going to have the target distribution you wanted with very simple conditions. For example, I think we can show that if the density function exists with a finite second moment, then we're okay here. Okay. These are some pictures that Huang produced, and there are some theoretical considerations. I won't get into this too much, the theory here, but there are a lot of sort of unknown things that we don't know. But one important property of this flow is really a random map. Okay, so it maps from data distribution to Gaussian, and it's invertible, and then from Gaussian to data distribution. So you can actually transform. You can add an image, use this kind of flow map, transforming image from one type to another, and so on. So it's a very flexible way of doing image editing, doing a lot of work with image. These are some of the results that basically kind of regularity of the solution to that ODE. Again, I won't get into the details here, but one thing I just want to mention quickly is I think a lot of the AI models now provide us with some tool to deal with some high-dimensional statistical problems in a non-parametric setting. For example, testing of conditional independence. Okay, we know that's a very difficult problem, actually, in particular in high-dimensional case in the non-parametric setting. And so what we did here is to use normalizing flow to transform conditional independence to standard independence. Okay. So basically, if I have a flow model, then define that C and eta that way, then this conditional independence becomes standard independence. So dealing with conditional independence, we can change that to the usual independence problem. Okay, and then that simplifies the problem. And so this is based on the flow model to construct that transformation. And of course, this is very traditional statistical. A lot of work on this in the literature, and we actually did a lot of comparisons with different approaches. And the overall conclusion is that if you use this flow model, the basic idea is really we transform a high-dimensional arbitrary distribution random variables to Gaussian. Okay, so that conditional independence becomes approximately independence in a Gaussian setting, and that makes the problem much, much easier. And then in terms of power, in terms of type 1 error comparison, it looks pretty reasonable. Okay. The third example that I want to share with you is, I think large model is a very powerful tool for doing dimension reduction, for constructing data representation. Okay. So the basic idea is very simple. Okay. Again, I want to learn a conditional distribution. What we do is I can use a representation that R of X here. The R, if it's a deterministic function, we know that is always true. Okay, so that's an exact equation here. Doesn't matter what R is, okay? Then I have that decomposition. Now, in particular, if R is lower dimensional, then the task of learning the conditional distribution is divided into two steps. First, the conditional distribution of Rx given C. Now, Rx is in a lower dimensional space, so it's easier to learn that conditional distribution. Secondly, given a representation of X itself, we already know much about X, so that distribution is also easier to learn, okay? So we can use this kind of very simple decomposition to do that. Now, the question is, how do you construct an effective R function? Well, for some data, we have some experience with protein data. If you have a foundation model, actually, like AlphaFold or ESM2 give us a way of obtaining a lower dimensional representation of high dimensional protein sequence, okay? So the foundation model can be used for that construction. I don't need to talk about the importance of protein, but basically the question is, given certain functions, for example, maybe I want that protein to be anti-certain bacteria and so on, right? So that when I do drug design that has that desired function, then this is my condition. That's my protein sequence. And then once I have the sequence, I can use AlphaFold to predict the 3D structure. Okay, so again, I'm using this decomposition. Actually, we are working with a lab for drug design. This is the public data because they don't want to make their data public at this point. It turns out to be very helpful. That's why they collaborate with us. Otherwise, they don't even want to talk with us. But anyway, so in this particular data example, we have this lysosome. Okay, it has certain functions, like oral disease, cancer, and antivirus, and so on. Okay, certain functions, but they are from chicken or goose. So you don't want to use that directly on human. So basically, you want to generate, this is like a targeting, target search phase, right? You want to generate a lot of sequences, and then in the lab, you need to do certain experiments to test whether they have side effects, okay? So basically, for protein data, the typical length is 2042 amino acids. Okay, we know there are 21 kinds of them, right? So the dimension of the sequence, the dimension of the data is about 40,000. With only about 2,000 data points, you're not going to be able to train a generative model. So what we did is to use a large protein sequence model to reduce the dimension here. Okay. So this is ESM2. This is another, it's easier to use because we have some limitation. AlphaFold is not that easy to use, but ESM2 is particularly good for protein representation. So we use this to reduce the dimension of the sequence data and then train a diffusion model at the sort of latent space and then use a conditional gain to get back to the original sequence and then use AlphaFold to predict the 3D structure. So that's the workflow. And all this protein sequence data, I think Hong mentioned, those sequence data, they have the same architecture as large language models. There's no really much difference there. Okay. So these are some examples. The top ones are the real 3D structure. The bottom ones are we use the function of the real data and then use that as condition to generate a sequence and use AlphaFold to predict 3D structure. And they look reasonably okay. Because we need to do this with the lab people. They want to look at the 3D structure, to look at all kinds of things. But this is the main thing they want to look at. Okay. Also, we have some comparison with some other methods in the field, and it seems to work pretty reasonably okay. All right. The fourth example I want to show you is synthetic augmentation. I think this is becoming very, very important because as we have more and more generative models, a lot of the data are synthetic, whether you like it or not, right? Okay, so for example, for image data, there are a lot of synthetic. Sometimes you cannot even tell what's the difference between synthetic data and the real data. Okay. So here, again, we're using this image data as an example, but I think the principle is general, okay? So for image data, there are people looking at this. For example, in this paper, they did a lot of experiments. In particular, if you do generative model with image data, at a certain stage, the model will collapse. Basically, the generative quality becomes very bad. Actually, as you can see from the images there. Okay, so if you don't, if you're not careful about how to use synthetic data, it becomes a problem. Okay, I think Xiaotong did a lot of work on this, but we look at this from different perspective. Okay, so basically this is our very simple formulation here. Okay, so we assume we do have some real data. Okay, it's not total synthetic data. We know we have a small set maybe, but we also have synthetic data from some data generative model. Okay, we don't necessarily know that model. Now, the standard practice is basically just combine them, and then you do the analysis. However, if you look at this one a little bit, you can tell that this combined data can have a distribution which is very different from the real distribution. So if you train based on this model, your target, what you're targeted on, is not the same as what you wanted. Okay. So this is essentially, that's what people have been doing. It's called synthetic data augmentation. What we propose here is we actually want to do the right thing. Okay, we want to have a model that formulates the problem in the right way so that we know we're doing the right thing. Okay, so this is our formulation. So basically, we're going to associate with each sample with an indicator, whether it's synthetic or real. Okay, and then I know with this. If I do this, then this conditional distribution, when y is 0, is my real data distribution. Okay. So what we do is we did a lot of experiments so far. We actually mainly did use a image data to generate to learn a conditional diffusion model here. Just show you some examples. Okay. So this is a CFR10 data, and this is based on just original data, 1,000 sample. This is based on synthetic data. We trained a diffusion model with 10,000 images here, and use diffusion model. And then actually, I think use 50, because the total sample size is 60,000, right? There are 60,000 CFR10. We use 50,000 samples to train a diffusion model, and then use that diffusion model to generate 10,000 synthetic data image, and then combine them to generate, this is the synthetic data augmentation, and this is our method, use the same synthetic data, okay? So in this case, the synthetic data is very similar to the real data. So as you can see that if you use synthetic data, it does improve the quality of the image in terms of the FID score. FID score is a commonly used metric in the image data analysis to measure the sort of similarity between generated data and the real data. Okay, so the smaller the better. So what we have here is the standard synthetic augmentation approach is very similar to ours, or ours is very similar to that. So this is one case. Another case I want to show you is now if I use a large model to generate some images. In particular, the prompt we use. We use a lot of this word here: digital single lens reflex camera. Okay, that's a particular camera. So it generates images that has this feature, and then we use GPT to write over 1,000 prompts for this image generation here. Okay, so large model can be very useful in this case. Now, this is the model generated with the 1,000 real data. This is synthetic data. As you can see that if you just pull the synthetic data with real data, the quality of the image don't look like the real data at all. This is based on our approach. And also you look at this FID score, there's a huge sort of increase in the FID score. That means the quality, the generative quality is very bad there. But ours, there's still some improvements. Okay. Actually, if you look at this real image, it seems like it's doing well. This is one lesson we learned with the diffusion model is that actually, if your sample size is small, it's going to basically memorize your data points, okay? So for example, these are real data. We actually looked for the images in the real, this is our generated data. We look for the real images that are mostly correlated with the real generated one. Turns out they're exactly the same. So there's this model collapse in this diffusion model with just 1,000 data points. But with our model, we don't see that problem. Okay. All right. I think the last one, I won't spend too much time, but basically, I think a large language model is also going to help statistics in terms of data analysis. So in the last couple of years, we started to develop a system to do data analysis. My first motivation is that because I remember when I write code, just write our code, for example, to do a plot. It took me a long time, coding and everything. So I thought, can we use large language models to help us to save some time? That's my first motivation. The second motivation is because I teach a lot of introductory statistics courses to non-statistical majors. It's a challenge to get them to do some data analysis. So so I said, okay, let's try some. Maybe we can use large language models without coding to help these students to learn some statistics, because if they don't touch any data, they won't learn anything about statistics. So I always felt very important to push the students to really do some data analysis. That's my two main motivations to get this started. But so this system is really for data analysis, but now we have some capabilities. For example, it has certain capability for reasoning, doing some method recommendation. And also I'm really pushing for doing good visualization, because I think visualization is very, very important. Another thing that we're starting to think about is to connect this system with larger models, so that to make it easier for people to use foundation models in their analysis. All right, I won't all right, so this is I won't get into that. Basically, it's like an AI agent system. This is the algorithm. And I do have like a 2 minutes video. Maybe I'll skip the video. Okay, you can watch it online. I'll skip the video here. All right. So basically, the basic message is that I think large model is a statistical model. It's really very helpful to statisticians, because people already train a model there, right? Why not use them? So it makes use big data much easier in some sense. It bridges data with statistics. But there are many problems. For example, the larger model you're using may be trained on different kind of data, maybe biased. There are a lot of heterogeneity issues that people have been going to also talk about. Many issues, right? And computing resources, software. And another thing I think is worthwhile for us to think about is what kind of statistical properties we can get from those kind of approaches. Right. And finally, I want to, in particular, thank my collaborators here. The first project is really, as I mentioned, Huang Di and Li Ting. And then the second one is Gao Yuan. Gao Yuan did a lot of work on normalizing flow, ODE flow, theoretical properties, and He Zhenxuan, those are students. And the protein data is mainly done by Ren Chenyu. And the image, the synthetic data problem is done by Gao Yuan and Zhou Xueyu. And then the lambda coding is mainly done by Sun Maojin, but now we have two more people. He started this, and so that's why he's the only student on the paper. And then Han Ruijian, Jiang Pinyan, Qi Houduo, and then Sun Defeng, and then Yuan Yancheng. Qi Houduo and Sun Defeng, they are, and Yancheng, Yuan Yancheng, they are applied mathematicians. Part of my appointment is in applied mathematics. I find it's very useful to actually talk to those people. And these are some of the references. All right, thank you so much.
We've already run out of time, but maybe one question? Yes?
Many of these diffusion models